Hi. The first part of the engineering mechanics was static, which is concerned with the equilibrium of bodies at rest or moving with constant velocity. Dynamics is the subdivision of mechanics that is concerned with the motion of the material objects in relation to the physical factors that affect them, such as force, mass, momentum, and energy. In other words, it's a branch of classical mechanics that is concerned with the study of forces and their effects on motion. In this course, we will start with kinematics of particle. Dynamics deals with the bodies having accelerated motion. We divided it into two sections, kinematics and kinetics. Kinematics is the study of the geometry of motion of particles. Kinetics deals with the analysis of forces causing the motion. The objects such as rockets, projectiles, vehicles are considered as particles, and the motion of their bodies is characterized by motion of their mass center, and any rotation of their bodies is neglected. Rectilinear kinematics represents continuous motion. A particle can move along either a straight or curved path. We will start with rectilinear straight line motion. The kinematics of motion is characterized by specifying the particle's position, velocity, and acceleration at any instant. Displacement is defined as delta S, which is equal to s dot minus s. Velocity v is defined as ds over dt. The symbol of acceleration is a. A is equal to dv over dt, or we can write acceleration also as a function of displacement as d square s over dt square. Velocity is also written as a function of time. As initial conditions, we can assume v is equal to v0 and t is equal to 0. From the acceleration equation, we can extract dv is equal to a dt, and when we integrate this equation, substituting the initial conditions, we can obtain v is equal to v0 plus at. It is at constant acceleration. Position is also written as a function of time. V is equal to ds over dt, and when we extract ds, it is equal to v dt. When we integrate this equation substituting v0 plus at into velocity v, we obtain the equation s is equal to s0 plus v0 t plus 1 half at square. Now we will write velocity as a function of position. As initial condition, we assume v is equal to v0 at s is equal to s0. Velocity v is equal to ds over dt. Acceleration a is equal to dv over dt. When we extract dt from both equations, we obtain ds over v is equal to dv over a. From that equation, it is found v dv is equal to a ds. When we integrate this equation, it is written v square is equal to v0 square plus 2a s minus s0. This equation shows velocity as a function of position. Now we will solve an example question on rectilinear kinematics continuous motion. A particle travels to the right along a straight line with a velocity v is equal to 5 over 4 plus s meter per second, where s is in meters. Determine its position when t is equal to 6 seconds if s is equal to 5 meter when t is equal to 0. Now I will explain the solution. Velocity v is equal to ds over dt, and when we extract ds, ds is equal to v dt. When we substitute 5 over 4 plus s into v, we obtain 4 plus s ds is equal to 5 dt. When we integrate this equation by writing s0 is equal to 5 meter and t is equal to 6 seconds, the solution of integral is specified below. By solving the integral, we obtain the equation s square plus 8s minus 125 is equal to 0. When we calculate discriminant, it is found 564. When we solve the roots of the equation, we obtain s1 is equal to 7.87 meter, s2 is equal to minus 15.88 meter. Since the particle moves to the right in straight positive direction, the result of the problem is 7.87 meter. Up to now, rectilinear kinematics continuous motion has been addressed. Now I will explain rectilinear kinematics erratic motion. Erratic motion occurs when any one of the motion characteristics such as displacement s, velocity v, acceleration a is not continuous during a certain time period. The motion of the particle is described using graphs showing the relationship between any two of variables a, v, s, t. The relationship between these variables is established by using these kinematic equations. A is equal to dv over dt, v is equal to ds over dt. When we extract dt from both equations, we obtain A ds is equal to v dv. We will understand rectilinear kinematics erratic motion better by solving this question. A two-stage rocket is fired vertically from rest with the acceleration shown in the graph. After 15 seconds, the first stage A burns out and the second stage B ignites. Plot the Vt and St graphs which describe the motion of the second stage for t from 0 to 40 seconds. The acceleration diagram AT of the rocket is presented in the picture. As shown in the acceleration diagram AT, the rocket accelerated from 0 to 15 meters per second square in 15 seconds. And between 15 and 40 seconds, the acceleration A is equal to 20 meters per second square. First, we need to find velocity at 15 seconds, and then we will calculate velocity at 40 seconds. Acceleration A is equal to dv over dt, and from that equation, if we extract dv, it is equal to A dt. When we integrate this equation for time interval from 0 to 15 seconds, by substituting A is equal to t, the solution of the integral is specified below. The velocity at 15 seconds is calculated as 112.5 meters per second. In order to calculate velocity at 40 seconds, we will use the equation v2 is equal to v1 plus a delta t. From that equation, the velocity at 40 seconds is found as 612.5 meters per second. In order to plot the displacements ST graph, we need to find the displacements of the rocket between time interval 0 to 15 seconds and 15 to 40 seconds. First, we will find the displacement between 0 to 15 seconds. Acceleration A is equal to dv over dt, and when we extract dv, it is equal to A dt. And when we substitute A is equal to t to that equation and integrate it, we obtain velocity v is equal to t squared over 2. From the equation velocity is equal to ds over dt, when we extract ds, it is equal to v dt. And when we substitute t squared over 2 into velocity v, the solution of the integral is specified below. Writing S0 is 0 for t0 is 0, the displacement at 15 seconds is calculated as 562.5 meters. In order to calculate the final displacement at 40 seconds, we will use the equation of velocity as a function of position. The solution of the integral is given below. We will substitute v1 is equal to 112.5 meters per second, v2 is equal to 612.5 meters per second, s1 is equal to 562.5 meters, a is equal to 20 meters per second square into that equation. As a result of the final calculation, by substituting velocities v1, v2, displacement s1, and acceleration a, the final displacement is calculated as 9,625 meters. As a result, we found velocity v1 at 15 seconds and velocity v2 at 40 seconds, displacement s1 at 15 seconds and displacement s2 at 40 seconds. The plotted Vt diagram and displacement St diagram are presented. When we look at the velocity Vt diagram, the velocity increases between 0 second and 15 seconds in a parabolic shape, and the velocity increases between 15 seconds and 40 seconds as a straight line. When we look at the displacement St diagram, the displacement increases in a parabolic shape, and when we look at the slope of the curve between 15 seconds and 40 seconds, it is much more than the slope of the curve section between 0 and 15 seconds.